Hello friends, today we are going to see about the virtual displacement, principle of virtual world and D'Ambert's principle. Let's see virtual displacement. Virtual displacement or imaginary displacement. These displacements are infinitesimal and all instantaneous on the other side. Real displacements take a finite time for their realization. This virtual displacement are given the system in such a manner that the constrained force do not do any work. See, the virtual displacement consider only for the coordinates like x, y, z, but not depend upon time. Again, in the virtual displacement, the force of constraint is equal to 0. You can see if you say this x along the time t. Now x of t from the point A to B, that is the actual path. Now you can take a neighboring path as like this x of t. So the neighboring path is noted as x dash of t. Now the displacement between x of t and x dash of t is noted as delta x. That is virtual displacement. Now, dear friends, the virtual displacement at this endpoints is equal to 0. Delta A equal to 0, delta B equal to 0. Now you can see the principle of virtual work. When a particle is given virtual displacement by a force, the amount of work done is said to be virtual work. So we know that work is equal to force into displacement. So virtual work is given virtual displacement by a force. Work as force into displacement. Now you can take the force acting on either particle as Fi vector. This has two components. External force, that is Fi vector over E external, and the second one is the force of constraints, small Fi vector. Now you can write this Fi vector is equal to external force plus force of constraint, Fi vector. Now, the virtual displacement you have to take as delta Ri vector. Displacement is notated as Ri and virtual is noted as delta. So, virtual displacement you can take as delta Ri vector. Now, you can take that work, virtual work. Virtual work you might be know that force into displacement. So, here you are taking the force as Fi vector over E external plus force of the constraint into displacement is delta Ri vector. That is virtual work. Now, in the equilibrium position, you know that the total force is equal to 0. So the total force Fi vector, the total force is equal to 0. Now delta Wi means the work done is equal to force into displacement. This is virtual displacement, hence you have to take the notation as delta Ri vector. Right? Now Fi vector equal to 0. Substitute here, that will be equal to 0. Now summation I is equal to 1 to capital N. Capital N, that's denote for I particles, N particles. Okay, summation I is equal to 1 to N delta Wi is equal to 0. And you know that delta W is nothing but force into displacement. So Fi dot delta Ri is equal to 0. Again, Fi vector is nothing but Fi over E plus Fi dot delta Ri is equal to 0. Now the virtual displacement are such that the constrained force. This will be do not do any work. So summation I is equal to 1 to n Fi vector over E delta Dri vector is equal to 0. Already in the first section itself we see that virtual displacement force of constraint is equal to 0. You can refer. The total amount of work done by the external force for the virtual displacement of n particles is known as virtual work. The total amount of work done by the external force, total amount of work done virtual displacement of n particles over the external force. This is given in wordings. Total amount of work done by the external force for the virtual displacement of the n particles is known as virtual work. And that total virtual work is equal to 0. This is the principle of virtual work. Now you can see D'Ambert's principle. The principle of virtual work is applicable to the system in the equilibrium states, but the system may be in state of motion. The principle of virtual work was modified by two new principle is known as D'Amber's principle. You can see the equation of the motion already in the first. We can know that Fi vector is equal to Pa vector dot. That is nothing but force is equal to rate of change of linear momentum. That is notated here as Pa vector dot. Now, in the first part, we see that virtual displacement, virtual work. There you can see the force is equal to Fi vector over E plus Fi vector. That is nothing but external force plus force of constraints. Force of constraints and external force. Now, that's equal to 0. See the last slide, then you can understand that's equal to 0. Now you are taking the virtual displacement. So take dot delta Ri vector, dot delta Ri vector, so that's equal to 0. Now you are summing over for all particles. So summation I is equal to 1 to n is equal to 0. Now we know that virtual displacement, the force of constraints is do not do any work, that is force of constraint equal to 0. At the beginning of this virtual displacement, we noted that force of constraint in the virtual displacement equal to 0. Now this part will be equal to 0. So the resultant one summation I equal to 1 dn Fa vector over A minus Pi vector dot delta Ri equal to 0. This is known as the D'Albert's principle. Now let's see. Discuss the motion of the particle in a space using a Lagrange's equation. So in a space, so you can take x, y, z be the generalized coordinate of space. You can take r vector equal to xi vector plus yj vector plus zk vector. Now velocity v vector is equal to dr by dt, that is first derivative. Velocity equal to rate of change of displacement. So that just differentiate this one. X dot I vector, y dot j vector, z dot k vector. This dot represent nothing but differentiated dx by dt, dy by dt, dz by dt. Now, here the question is discuss the motion of particle in a space using Lagrange's equation. So the Lagrange's equation is d by dt dou t by dou x dot minus dou t by dou x is equal to qx. Again dou t by dou t, d by dt dou t by dou y dot minus dou t by dou y equal to qy. Again d by dt dou t by dou z dot minus dou t by dou z equal to qz, because it consists of three generalized coordinates. So for that you need here t. So here t is the kinetic energy, which is 1 by 2 half mv square. Now apply the value of v. V square. V square means v vector dot v vector. So by deriving you will get x dot square plus y dot square plus z dot square. Now you can take force is equal to here three coordinates. So force x I vector plus force y j vector plus f z k vector. Now you can write this, substitute all this in this Lagrange's equation of x, y and z coordinates. Let's see students. Okay. d by dt dou t by dou x dot. Already you know that t is equal to 1 by 2. Already you know that t is equal to 1 by 2 m x dot square plus y dot square plus z dot square. Now if you differentiate with respect to x dot, what will be 1 by 2 m 2 x dot, other will be 0. Similarly, dou t by dou y dot, you will get 1 by 2 m 2 y dot. Again, dou t by dou z dot, you will get the another one. Now, dou t by dou x is, here no x is there, so that will be considered as 0. Again, dou t by dou y, here there is no y, so it will be considered as 0. Let's see here. Right. Dou t by dou x, dou t by dou y, and dou t by dou z equal to 0. Now substitute all this in the Lagrange's equation. dt by dt mx dot, and the second one equal to 0 is equal to qx, and that is notated as fx, because q is the generalized force. It is noted as generalized force. So that is fx. Similarly, substitute in the next equation d by dt ut by dou y dot is my dot equal to qy, and that is noted as fy because generalized coordinate q is noted as f. And d by dt m z dot equal to q z equal to f z. Now you can write this one. D by dt of x dot is simply x double dot. So m x double dot equal to fx, m y double dot equal to fy, and m z double dot equal to fz. So this is the required equations of motion in space using Lagrange's equation. Thank you.